We will use this live editor to work through this example. For those of you who are not familiar with this feature, Live Editor is an interactive way to write code and generate computational narratives that are easy to share and communicate. In the hard sounds datasets, each recording is an audio file that has a normal and abnormal label. Let's start by plotting and listening to abnormal hard sounds. Matlab provides tools like audio read and audio player, which makes it easier to play with such audio files. Now let's listen to what a normal heart sounds like. Okay, that was a little bit quick, so let's play them again. So here is the abnormal heart. And here is the normal heart. While we're not experts, we certainly notice some differences. The abnormal heart seems to have higher frequencies and the noise-like quality in between beats. The normal heart, on the other hand, is more irregular with silence between beats. Now we have some ideas of what the heart sounds like. Let's take a look at the signal in the frequency domain. The signal processing toolbox requires an app called Signal Analyzer that enables us to do this without writing any code. So let's open up the app. In the Signal Analyzer app, we can take a look at the two signal sides side by side. On the left side we have the normal heart sound signal, and on the right side we have the abnormal heart sound signal. We can clearly notice the differences as we saw earlier in the live editor. Now we can take a look at our power spectrum for both these signals. We immediately notice that the higher frequencies in the case of abnormal heart sounds. We can also use the panner feature, which allows us to take look at the short segments of the signal at the time and essentially kind of go across the signal and see what changes and if there are any changes across the power spectrum as we go across the signal. Again, we observe the presence of higher frequencies for abnormal heart sound signal. Now that we have some idea of what the signal looks like on the frequency domain, let's go back to the live editor and work on feature extraction. Next, let's start preparing for the pre-processing stuff. Let's take a look on how the files are organized on the state set. The dataset we have using in this example includes more than 3,000 files separate across the multiple folders. Two main folders under status set training and validation. Under the training folder, we have multiple folders from A to F, each of which can take several hundred files, corresponding to the individual heart sound records. This folder also contains the reference file, which includes the label associated with each of these recordings. So rather than writing code and navigate through those folders and accessing the data files, we will create a file data store object. A file data creates a collection of files and uses a read function to load the files sequentially into memory processing. This enables us to work with large collections of files without worrying about the number, organization, or the naming of the files. Next, we will read the reference files and create a table with the file names and corresponding labels. We will use the reference table during feature extraction to build the feature table. So we now move from accessing Explorer stage to the pre-processing stage. In this step, we will process and extract a set of features from the raw heart sound signal using 5-second non-overlapping windows. Both of the computation happens in extract feature function. Let's take a look at it. In order to capture as much relevant information as possible, we extract a large set of about 71 features from each window. The extracted features include some of the statistics like mean, median, or standard deviation, features from the frequency domain like the maximum frequency or spectrum frequency, as well as features from the wavelet analysis. We also extract features from the speech processing domain called the male frequency subcoefficients. All these features capture information from different perspectives that they may or may not be relevant to our problem. So let's go back to the library where we extract the features from our dataset. Depending on how many features you are extracting and the size of your dataset, feature extraction can be a time-consuming step. In order to speed up feature extraction, we're going to use PAR4 from the computing toolbox to distribute contributions about all over the course, either locally or computer cluster. For this example, I have captured the feature table, so I did that earlier and I skipped future construction and load up recalculated feature set. Let's take a look at the features. Here we can see the first file observation from the future table. So the table is organized as a column corresponding to different features or predictors, and rows corresponding to individual observations. For each observation, the final column corresponds to class, which could be normal or abnormal. Our next step is to quickly train and compare multiple classification algorithms. The classification learner app has been designed exactly for this purpose. So let's launch the app and take a look. In the classification learner app, we can start a new session. The first step is to select the table or matrix to work with. So in this case, we're going to use the futures table. The second step is to assign the variables and predictors or responses or ignore them. In this example, we're going to assign to all the variables predictor, and to the last one going to be the response, which is class. The next step is to select the validation strategy. Because we have lots of observations in this example, we're going to use the validation with 50% of the data for training and 50% for testing. So let's start the session. So let's see, the first view that we get from the classification learner is a scatter plot. A scatter plot has one feature on the x-axis and the other feature on the y-axis. The points and the scatter plot are labeled by the different classes. So it is a good view for us to quickly look at the features and see which features might carry some useful information. If you have lots of features, like in this case, it's hard to actually look at the possible combinations. This is a very high-dimensional data set. To explore this data set at the scatter plot, let's start training some classifiers. So in the classification app, we have access to a number of different classifiers. We have access to decision trees, logistic regression, support vector machines, nearest neighbor classifiers. So this is just sample of example classifiers. So another nice feature of the classification learner is that you can select this classifier individually, or you can choose to trade multiple classifiers. For example, I can select all support vector machines and use the ability of the classification learner app to train the classifier to quickly train and compare their performance. So I have access to 12 cores on a cluster, and I can use all of them to train my classifier pretty quickly. So here are training results. Show that the cubic SVM as well as the Gaussian SVM and the quadratic SVM seem to give good performance. So let's take a look at the performance numbers. So if you take a look at the confusion matrix, This tells us that the misclassification for the abnormal class is significantly higher compared to the normal class. And this is most likely because of the imbalance in the number of observations. So we can see the number of observations from the normal class is significantly higher than the abnormal classes, which increases the likelihood of all classifiers is bias. The other aspect is consider here that in the problem that we're working on, it might be better to misclassify normals instead of misclassifying abnormals. That is, it's better to be more accurate at classifying abnormal instead of misclassifying normals as abnormals, because this is a screening tool, and the consequence of not screening someone who is abnormal is significantly higher compared to screening someone who is normal and then figuring out they don't have medical conditions. The ROC curve is another useful tool for assessing performance. So here we get an idea of the trait between the true positive and false positives. In this example, as I said earlier, it might be okay with the higher rate for false positive in favor of increasing the true positive rate. So let's go back to the live editor and solve these issues. In order to train the classifier programmatically, let's first split the data set into training and testing 50-50 ratio. The function CV partition makes it easy to create such splits. If we take a look at the number of observations for normal and abnormal classes, we can clearly see the imbalance that could lead to a biased classifier. This is a common challenge when it comes to supervised learning. So let's now train a classifier and try to take it into account that there are some imbalance issues. To encounter the imbalance, we can assign higher misclassification costs associated with the class, with the features from the observation. For now, our example, we are interested in maximizing the detection for true positive for the abnormal class, so we will assign a 10x cost with the misclassification. So in other words, we are going to tell the classifier it's okay if someone was normal gets misclassified instead of abnormal, rather than the other way around. However, if the positive rate is too high, the examination would become useless, so we try to achieve a good balance between higher accuracy for the abnormal class and governance for false positive. The normal class, another challenge is associated with the training is by hyperparameter tuning. Most classifiers have one or more parameters that can be tuned to achieve a better fit. In the case of support vector machines, one can tune box constraints, kernel scale, and kernel functions. Tuning parameters manually can be a tedious process and lead to suboptimal values. On the other hand, exhausting quick search approaches and time-consuming for machine learning. Matlab provides visual optimization based by hyperparameter tuning that is coupled with the fit function API. So specified name value parameters in the training function is a method search through the parameter space and defines the optimal values for the hyperparameters. So let's take a look at how the hyperparameters tuning work in VisionWorks. The method works by a Bayesian model of the function model, trying to minimize and uses selects the next 2 points evaluating the function. This approach allows Matlab to quickly search the parameter space to identify the optimal parameters values. This method is specifically designed to minimize the number of function evaluations and is very efficient compared to search other standard optimization methods. So we can see here the method has completed all the iterations and has found the optimal value for box constraint and kernel scale, which it has automatically selected for the classifier. So let's go back to the editor and look at the performance that would had been trained and misclassification costs and the hyperparameter optimization. I have saved previously, so instead of training it here, I'm going to just load the classifier, and we can see we can look at the performance. So let's see. So here is a confusion matrix as a heat map, and we can see that by tracking continuous classification costs, we have been able to significantly increase the accuracy of the abnormal class, and this has come at a cost for the normal class, which is now significantly misclassified normal as abnormals. Let's see what we can do about this. Potential reason for the poor performance of the classifier could be overfitting. One approach for dealing with overfitting is to use a number of parameters or features by performing feature selection. Feature selection is an important step in machine learning workflow, and it was all solely in the saving in terms of computational costs and storage requirements, but also results and helps less likely overfit. In this example, we will extract 71 features. There is a potential there might be features which are either redundant or not carrying any useful information. So let's go back to the pre-processing step and unuse pre-processing selection technique called neighborhood component analysis, or NCA. NCA is a powerful technique for feature selection as it is able to handle very high dimensional data sets significantly. Higher dimensions than that we are dealing with, as well as data sets are extremely large observers. The other factor here is that as a user, you have control over the lambda parameter, which is the regularization parameter. And it allows you to control this process as well as minimize tendency in the selector feature by increasing the value of lambda. So let's go to the feature selection on our data sets and see which features are selective. So here the NCA method went through our feature and identified all the 71 features, and 11 features are carrying useful information. So now let's go ahead and train a classifier model with only these 11 selective features, and we use the selective features and also perform hyperparameter optimization to train a new classifier. So here are again, as before, I have saved previously trained classification models trained on the selected features. I'm going to simply load it and look at the performance of this classifier. So if you take a look at the performance of the abnormal class has improved slightly, but there is a significant improvement in the terms of performance of the normal class. This indicates that there was a potential for overfitting, which has addressed the feature selection. So at this point in our analysis, we might be happy with the performance we are getting from the trained classifier. All trained classifier is able to accurately detect more data, 98% of the abnormal cases and almost 75% of the normal cases. The 25% of the misclassified rate of the normal cases can be okay, as it just is a screening test, and this case will be further evaluated by experts. The next step for us is to deploy the analytics. Because the goal is to use hard sounds for diagnosis, one deep learning solution might be to deploy analytics to embedded system which can process data and provide results immediately. Matlab provides support for code generation, which makes it easy to generate code to integrate in embedded targets. Let's take a look at this process. This process consists of 3 steps. First, we save the train model by using save compact model methods. Next, we create an inter-point function, in this case called classify hard sounds. Classify hard sounds is a function that takes raw sensor data as input and produces the classification label of normal and abnormal after processing the raw sensor data for feature extraction and train classification of the model. The final step is to use the coder app to automatically generate this code. So let's take a look at what the coder app looks like and the steps involved. The Matlab coder app provides a guided step-by-step guided to generate standalone C or C++ code from Matlab. So the first step is to select the entry points. The next step is to define the import types of app. Can do automatically by evaluating the entry points. For this example, we want a signal to be fixed length. Next, the app checks for any runtime issues and places for fix bugs and the functions. So looks like we don't have any issues. The final step is to generate a C or C++ code. The app has successfully generated a code which can now be deployed to embedded targets. The final step is to validate the generated C code by processing files from the validation set. This can be done using the max file as an interface between Matlab and the SQL. In this plot, we can see the various hard sound signals as well as actual and predictive labels. So near to the performance of our testing set, what's the errors and the associated misclassification as normal or abnormal.